What's up, everyone? Welcome back. We've got a video on a special kind of factoring today. And we're going to be identifying two cases that, kind of come up again and again in mathematics and that we use strategically later in further math classes and potentially, in further lessons here in this course as well. Now, these special cases can be factored by the previous methods that we've learned in this video series. However, if you recognize these special cases and you can identify them quickly, it makes factoring much, much faster. So you're able to take this shortcut and not go through the conventional methods of factoring that we've learned. So what I'm going to do in this video is I'm going to introduce, the case, and then we're going to show that it repeatedly you're going to get the same thing over and over again. It's going to sort of kind of get boring when you see it, and then you should be able to identify it from there. This takes practice. I don't expect you to get it the first time, but this is a great opportunity for us to explore these options. So let's take a look at this. This case is when we're multiplying two linear binomials, and the first term in each is just a variable, is the same, and the second term in each is the same. But the signs differ. And when we multiply this out, let's take a look for a sec. When we multiply this out, we get x times x is x squared. X times negative 9 is minus 9x. We get 9 times x is plus 9x. And we get 9 times negative 9 is negative 81. So we have our two like terms, or the two x terms. And since they are the same magnitude, they're both 9, but one is positive and one is negative, the coefficient is then 0, so the term goes away, and all we're left with is x squared minus 81. All right, let's do another one. How about like x minus 4 times x plus 4? Let's take a look at this one. X minus 4 times x plus 4. Again, x times x is x squared, and then we have plus 4x minus 4x minus 16, which ends up being x squared minus 16. These two terms we add together, the coefficient goes to 0, the term essentially disappears. So this is our first special case. When you have the first two things in the product the same, and then you have the second two things the same but differing by a minus sign, the middle terms will always cancel because the magnitude of these two numbers is the same. So the middle term is going to cancel out every single time, and what you end up with is really the first thing squared minus the last thing squared, and it's always negative because the signs are different. When you multiply a negative, you get a positive times a negative, you get a negative. Okay, this is the first special case. It is the difference of squares, and this basically says it all. And we can do this in two different directions. Like if we're going from here, from the left to the right, we are factoring. Okay, and that can really save you some time. And if you're going, this direction, we are expanding. We're multiplying these out. Some might call it foiling or something else. But so this can save us a lot of time going both directions if we are able to recognize it. And it is pretty simple. You get something squared minus something squared. Oh, I can just write it as the first something plus the second something times the first something minus the second something, and you're done. And you don't have to do the traditional factoring process. If you don't recognize that, you can do it by conventional methods, but it just takes longer. We're about to see that. So the difference of squares is the name of this special case. So here's how you do it. Pretty simple. Is the first term something squared? Yeah, it's a squared. Is the second term something squared? Yeah, it's 5 squared. Then I am done. I'm done. This is a plus 5 times a minus 5. I factored it. And we can check our work, right? Actually, I'm going to move this a little bit. I'm going to move this down here. Do some shifting around. I'm going to check my work just so, you can sit here and check as much as you want. A times a is a squared minus 5a plus 5a minus 25. Middle terms cancel out. We're left with what we started with. So we know that it works out. Now, if we were to do this by the old method, this would be the old way. it's not as intuitive, and it doesn't, we didn't see any like these on 7.4. So this is from section 7.4 video, if you want to go and rewatch that. To write this in the form, you know, a squared plus what ba plus c or whatever, it turns out the coefficient of my squared term is 1, so it falls into the 7.4 category. The coefficient of my linear term, or degree 1 term, there is no degree 1 term, so the coefficient is 0, so it'll be plus 0a minus 25. So if we're following that the steps we did in 7.4, we're looking for two numbers that multiply to negative 25 and add to 0. Well, two numbers that multiply to negative 25 to add to 0 are 5 and negative 5. So you can use the conventional method here, and it's really fairly easy, but you have to think about that middle coefficient being 0 for that to make any sense. So the old way still works. So let's take a look at this blue one. This one in blue here. Is the first term something squared? Well, it's a couple things squared, but that's okay. As long as we can write it as something in parentheses squared minus something in parentheses squared, we're good. Well, the second one's easy. 1 squared is 1. What squared is 64x squared? Well, 8 times 8 is 64, and x times x is x squared. So that's how we get our answer. And then we can take those two things and then just plug them into the formula that we had before. 8x minus 1 times 8x plus 1. You may be asking, Mr. Schlegel, why is the positive first here and the positive is second here in the blue example? Well, it doesn't actually really matter. The commutative property of multiplication says we can multiply two things in any order, so I can shift those around and don't run into any issues. Now, if I were doing this via the old methods, so the old way here, the old way still works. This is from 7-5. The reason this is 7-5 and not 7-4 is our leading coefficient is not equal to 1. 64x squared plus 0x minus 1. We're looking for factors of negative 64 that add to 0. Okay, two things that multiply to negative 64 and add to 0. That's going to be 8 and negative 8. So let me erase that. Try that again. That would be like 64x squared minus 8x plus 8x minus 1. GCF of the first two is 8x. So it's 8x times 8x minus 1. And we have 8x minus 1 here, so our GCF is 1. That's what they have in common, and it'll match up here, no problem. So we have these two factors that are the same, 8x minus 1, 8x minus 1. So it gives us 8x minus 1 times 8x plus 1. Oh, look, that's what we already have. So the old way works, it just takes way longer. If you can recognize the difference of squares, it's going to save you time. And we know time is money. So Mr. Schlegel's really, I mean, I'm just saving you money is what I'm doing. So if you can feel free to forward any of those proceeds on. No, don't pay me. I already, you know, I'm doing okay. But I was able to afford these Lord of the Rings cardboard cutouts, so doing just fine. Oh, let's take a look at this one in purple. This is two terms. It's a difference, but 50 is not a perfect square, and 32 is not a perfect square. So this must not be a difference of squares. It is a difference of squares. It is a difference of squares. The first term, well, the first thing you always have to do when you're factoring is check for a GCF. And there is a GCF between them. It is 2, and they also contain an x. So I can factor out a 2x from each term, and then what we have left is 25x squared minus 16. Both of those are perfect squares. Oh, so I can write this as 5x squared minus 4 squared. Sweet. That's a difference of two squares. 5 times 5 is 25. X times x is x squared. 4 times 4 is 16. So I can go straight to my answer, which will be 5x plus 4 times 5x minus 4. And that's factored. Doot, doot. Looking good. All right, you guys try this one on your own. Is this a difference of two squares? What are the things squared? Break it apart and go from there. You can unpause the video when you think you have an answer. What times what is y squared? That's a y. What times what is 400? That's a 20. It is a difference, two squares. Minus plus or plus minus, it doesn't matter. All right, so that's the end of special case 1. That's called the difference of squares. And again, we recognize that by seeing one thing minus another thing, and they're both perfect squares. Moving on. Okay. I'm going to talk about how to do this correctly. This is our next special case. And then I'm going to show you a common mistake that students make when doing this. Okay, here we go. All right, let's do this correctly. What does an exponent mean? It means that thing times itself, right? Squared means times itself. So x plus 3 squared really means x plus 3 times itself. There should be 2 of them in the product. So when you multiply these out, you end up doing x times x is x squared. X times 3 is plus 3x. 3 times x is plus 3x. And 3 times 3 is 9. Now we have 2 like terms in the middle, and you get x squared plus 6x plus 9. Pretty exciting. Okay, this should not be confused, and this is where people make mistakes. It should not be confused with what we did last unit with exponents. With exponents, we were able to just, there are 2 bases on the inside, we were able to go straight to the answer and say that's 3 squared x squared. But that has to do with properties of multiplication, right? When you just have multiplication, we can multiply in any order, because really this means 3x times 3x, so we can change the order up and write that as 3 times x, which is this. So we're able to kind of pseudo distribute out the powers. We can't do that here because we don't just have multiplication. We have multiplication and we have addition. So this is more complicated. We have to do the method that was taught in 7.2 for multiplying polynomials. You have to make sure we multiply every possible pair from the 2 groups. So that's where the mistake comes in. So the common mistake that students make is they go, this is a mistake, I'll just say common mistake. Common mistake is they'll say, oh, x plus 3 squared, that's x squared plus 3 squared. It's not, because you're forgetting the 2 middle terms. Not going to work out. So I'm going to put a big circle around this, put an x through it. That is not what we do. And it's actually made even worse when there's a minus, because people think this is a difference of 2 squares, and it's not. This is exactly like the case above. People want to just say, oh, it looks so much like this case. It's not. It's a separate case completely. This is a different special case than the one we were learning about before. This means x minus 7 times x minus 7. And so you'll notice whenever I have a linear binomial like this squared, we did first things, you got x squared, we got 3 squared at the end, but then the middle 2 terms were the same, right? So like right here, when we multiply this out, we end up with x squared, you end up with minus 7x, and then negative times a negative is a positive 49. So with this case, it's very similar. We squared the first thing, it went in the front. We squared the second thing, it went at the end, but it was positive. And then in the middle, we had the same thing twice, so we ended up just doubling the number that we had. So it's x squared minus 14x plus 49. So whenever you have a linear binomial squared like this, the middle term ends up pretty much double the product of these 2 things. So x times 7 is 7x, times 2 is 14x, right? Except it's negative. And then the last one is always just that number squared, but positive. This is the trick. And when I write it out in a rule form, it's oftentimes, it looks more confusing in the rule form than it does when you just look at an example. You can see that, you can see that in this case that it's just basically doubling that value that you have. So, and you can see that here in the equation. So if I say a plus b squared, let's start here and go this direction. This would be the expansion direction. This would be the factoring direction. So from the expanding direction, a times a gives us our a squared. b times b gives us our b squared, and then we have the two middle terms, which would be a times b and b times a. But a times b and b times a are the same, so we add them together, and you get double that value. Okay, here, a times a is a squared, b times negative b is positive b squared, same as the case above. Okay, but then we have minus ab and minus ba. Those are the same things. B times a is the same as a times b, so we can join them together to have be subtracting 2ab. So the expansion direction is pretty easy. It's the factor in the direction that kind of trips kids up a lot of the time. So when you're doing it this way, we can say, is the questions we ask are these? And I'm going to pause the video and I'll write them out, and then we'll come back and visit them in just a sec. So to identify whether or not something is a perfect square trinomial is what we call them. We call it a perfect square trinomial because it's this plus this squared or this minus this squared. The reason we call this, to check to see if something is a perfect square trinomial, we answer the following questions. And if all of them are a yes, then we can use this kind of little formula to factor quickly without doing the old method. And it's a shortcut, but it takes an eye, it takes some practice. We're going to look at a lot of examples. We may even see a little counterexample. So, is the first term something squared? We ask that question. Is the second term something? The answer is yes, you move on. If the second term something squared, answer that question, move on. And is the middle term twice the product of those two things? If you can answer yes to all those, it's a perfect square trinomial, and you can move forward and factor. Step 0, remember, is always to check for a GCF. So let's go ahead and see some examples of how we factor this and what it's going to look like. All right, so y squared plus 8y plus 16. Does it have a GCF? No. Is the first term something squared? Yeah, it's y squared. Is the second term something squared? Yeah, it's 4 squared. Now here we go. Is the middle term, 8y, twice the product of the two things inside the parentheses? Is it twice the product of those things that are being squared? Y times 4 is 4y, times 2 is 8y. Yes, so this is a perfect square trinomial. And so actually I'll come down here. It is a perfect square trinomial, so we can go straight to the answer. The middle term is positive. If you notice back at these equations, if the middle term is positive, that is the telltale sign of what is going to be inside the parentheses. If it's negative, it's going to be in over here. So we're going to do y plus 4 squared. And we can check our answer by multiplying out. Check ourselves so we don't wreck ourselves. It's kind of the slogan. That's y plus 4 times y plus 4, which is y squared plus 4y plus 4y plus 16. Hey, look, that's the same as what we have up here. Great. Now, if we were to factor this by the conventional or the old method, this would be from 7,4. Factoring using that old method from 7,4, we would say we need factors of 16. Factors of 16 that add to 8. Well, factors of 16 that add to 8, 1 times 16, 2 times 8, 4 times 4. Hey, we found them. It's 4 and 4, so we'd write this as y plus 4 times y plus 4, but that's just y plus 4 squared. It's y plus 4 times itself. So, pretty exciting. All right, yikes, this one. Okay, let's take a look. In blue, is the first term something squared? Yeah. It's 7x squared. Is the last term something squared? Yeah. It's 1 squared. Now we got to check. Is the middle term twice the product of this times that? Yeah, except it's negative. That's okay, because this is following the pattern for this blue example down here. So we're going to say, yes, this is a perfect square trinomial, because 7x times 1 times 2 is 14x. So we're going to do 7x minus 1 squared. Done. We don't have to do those conventional methods. I will show you that the old way still works. If we're going to do this the old way, we need factors, which is 7, 5, because our leading coefficient is not equal to 1. It was equal to 1 up here. We're going to break apart the middle term. That's the method that we're going to use. We're looking for factors of 49 that add to negative 14. So that's going to look like 49x squared minus 7x plus 1. We pull out the GCF of the first two, which is 7x. We have 7x minus 1 left over. And we pull out the GCF of the second two. Well, this is 7x minus 1. This is negative 7x plus 1. The signs are different. That tells us that we pull out a -1 as our GCF. And -1 times positive 7x is -7x, -1 times -1 is +1, so we can check our answer there. We have left 7x minus 1 times 7x minus 1, so the conventional methods still work. Okay, let's keep moving. You guys can try this one, maybe? Or do you have a you try down here? Try this one out, see if you can do it. Unpause the video when you're ready to see me work it. Here we go. We're going to start. First term something, or is there a GCF? 25 times 5? No, there isn't. First term something squared? Yep. It's 5m squared. Is the last term something squared? Yeah, it's 3 squared. Is the middle term twice the product of those two things? Let's see. 5m times 3 is 15m times 2 is 30. Yes, it is, so we're done. It is 5m and then a 3 squared. Take the sign of the middle term, negative. Done factoring. Okay, let's take a look at this green example. Take a look at this green example. Is the middle term, first term something squared? Oh no, we forgot to take out a GCF. So that's what I'm going to do first. They're all divisible by 5. So I'll pull out a 5. This is 5n squared. Or sorry, redo that. 5. Get out of here, 2. Just go on and get. Don't come back. 5, pull out a 5. N squared plus 8n plus 16. Did we already factor that one? Yeah, we did. We factored that one in black right there. It's basically the same question. First term something squared, yeah, it's n squared. Last term something squared, yeah, it's 4 squared. Middle term twice the product of n and 4, yep. 4 times n is 4, times 2 is 8n, so we're done. This is 5 times n plus 4 squared. Okay, we've got some more apparently. Let's keep going. All right, is this a perfect square trinomial? I think we're kind of beating a dead horse here. I think you probably have it or you don't. This is m squared. This is 12 squared. And then the middle term is twice the product, so we're done. This is m minus 12 squared. Negative 12 times negative 12 is 144, and then we have our two 12m terms that are going to add up to our middle term. So we've got it. All right, and that one's pretty straightforward. We'll just do it really quick. Is first term something squared? Yeah, it's c squared. Last term something squared? Yeah, it's 5 squared. Is the middle term twice the product? 5 times c times 2, 10. Yep. So it's c plus 5 squared factored, or c plus 5 times c plus 5. And this is n minus 12 times n minus 12. Okay. So what are a few ways we can identify which case we have? Well, the difference of squares, if we're factoring, let's talk about factoring. When we're factoring the difference of squares, typically it'll have 2 terms. And perfect square trinomial will have 3 terms. That's the big difference if we're factoring. Okay, so perfect square trinomial, you want to check. It's always going to have 3 terms, and trinomial, difference of squares is always going to be a binomial. So just look out for that. Okay, we can skip that, and your assignment's in My Open Math. I do want to make a quick comment, so I'm going to ready a question really fast and then kind of talk. All right, take a look at this one really fast. Is the first term something squared? Yeah, it's x squared. Is the last term something squared? Yeah, it's 2 squared. Is the middle term twice the product of these two? No, it's quadruple the product. So this one is not a perfect square trinomial, number 1, and we would need factors. In order to factor it all, we would need factors of 4 that add to -8, and they don't exist. So this one cannot be factored by the methods that you've been given. We would say that this is prime. There's no way for us to factor it. Just like saying, hey, I want you to factor the number 17. We can't break it apart. This is a prime number. Say the same thing about polynomials. Hope you guys liked the video. I had a lot of fun doing this one, and we'll see you next time.